some arbitrary function in this gigantic set of all functions from x to y, and we say that the PRF is secure if in fact a random function from x to y is indistinguishable from a pseudo-random function from x to y, namely when we pick a random function from the set SF. Okay, so more precisely, basically, again, the uniform distribution on the set of pseudo-random function is indistinguishable from the uniform distribution on the set of all functions. Let me be just a little bit more precise, just to give you a little bit more intuition about what I mean by that, and then we'll move on to actual constructions. So let me be a bit more precise about what it means for a PRF to be secure. And so what we'll do is basically the following. So we have our adversary just trying to distinguish truly random function from a pseudo-random function. So what we'll do is we'll let him interact with one of the two. So here in the top cloud, we're choosing a truly random function. In the bottom cloud, we're just choosing a random key for a pseudo-random function. And now what this adversary is going to do is he's going to submit points in x. So he's going to submit a bunch of x's. In fact, he's going to do this again and again and again. So he's going to submit x1, x2, x3, x4. And then for each one of those queries, we're going to give him either the value of the truly random function at the point x or the value of the pseudo-random function at the point x. Okay, so the adversary doesn't know which one he's getting. By the way, for all queries, he's always getting either the truly random function or the pseudo-random function. In other words, he's either interacting with a truly random function for all his queries, or he's interacting with a pseudo-random function for all his queries. And we say that the PRF is secure if this poor adversary can't tell the difference. He cannot tell whether he's interacting with a truly random function or interacting with a pseudo-random function. Okay, and we're going to come back actually later on and define PRFs more precisely. But for now, I wanted to give you the intuition for what it means for a PRF to be secure, so you'll understand what it is that we're trying to construct when we construct these pseudo-random functions. And I should say that the definition for a pseudo-random permutation is pretty much the same, except instead of choosing a random function, we're going to choose a random permutation on the set X. In other words, a random one-to-one function on the set X. The adversary can either query this random function on the set X, or he can query a pseudo-random permutation, and the PRP is secure if the adversary cannot tell the difference. Okay, so again, the goal is to make these functions and permutations look like truly random functions of permutations. Okay, so let's look at a simple question. So suppose we have a secure PRF. So we know that this PRF F happens to be defined in the set X, and it so happens, it outputs 128 bits every time. It so happens that this PRF cannot be distinguished from a truly random function from X to 0, 1 to the 128. Now we're going to build a new PRF. Let's call this PRFG. And the PRFG is going to be defined as follows. We say if x is equal to 0, always output 0. Otherwise, if x is not equal to 0, just output the value of f. So my question to you is, do you think this G is a secure PRF? Well, so the answer, of course, is that it's very easy to distinguish the function G from a random function. All the adversary has to do is just query the function at x equals 0. For a random function, the probability that the result is going to be 0 is 1 over 2 to the 128. Whereas for the pseudo-random function, he's always going to get 0. Because at 0, the function is always defined to be 0 no matter what the key. And so all he would do is he would say, hey, I'm interacting with a pseudo-random function if he gets 0 at x equals 0. And he'll say, I'm interacting with a random function if he gets non-zero at x equals 0. So it's very easy to distinguish this G from random. So what this example shows is that even if you have a secure PRF, it's enough that on just one known input, the output is kind of not random. The output is fixed. And already the entire PRF is broken, even though you realize everywhere else the PRF is perfectly indistinguishable from random. Okay, so just to show you the power of PRF, let's look at a very easy application. I want to show you that in fact pseudorandom functions directly give us a very simple pseudorandom generator. Okay, so let's assume we have a pseudorandom function. So this one happens to go from n bits to n bits. And then let's define the following generator. Its seed space is going to be the key space for the PRF, and its output space is going to be basically t blocks of n bits each. Okay, so you can see the output is a total of n times t bits for some parameter t that we can choose. And it turns out basically you can do this very simple construction. This is sometimes called counter mode, where essentially you take the PRF and you evaluate it at 0, you evaluate it at 1, you evaluate it at 2, at 3, at 4, up to t, and you concatenate all these values. That's the generator. Okay, so we basically took the key for the PRF and we expanded it into n times t bits. Okay? A key property of this generator is that it's parallelizable. And what I mean by that is if you have two processors or two cores that you can compute on, then you can have one core compute the even entries of the output, and you can have another core compute the odd entries of the output. So basically, if you have two cores, you can make this generator run twice as fast as it would if you only have a single core. So the nice thing about this is, of course, we know that pseudo-random generators give us stream ciphers, and so this is an example of a parallelizable stream cipher. And I just wanted to point out that many of the stream ciphers that we looked at before, for example RC4, those were inherently sequential. So even if you had two processors, you couldn't make the stream cipher work any faster than if you just had a single processor. Now the main question is, why is this generator secure? And so here I'm only going to give you a little bit of intuition, and we're going to come back and argue this more precisely later on. But I'll just say that security basically follows directly from the PRF property. And the way we reason about security is we say, well, this PRF by definition is indistinguishable from a truly random function on 128 bits. So in other words, if I take this generator and instead I define a generator using a truly random function, in other words, I'll write the output of the generator as f of 0 concatenated f of 1 and so on and so forth, using a truly random function, then the output of the generator using the truly random function would be indistinguishable from the output of the generator using a pseudo-random function. That is the essence of the security property of a PRF. But with a truly random function, you notice that the output is just truly random, because for a truly random function, f of 0 is a random value, f of 1 is an independent random value, f of 2 is an independent random value, and so on and so forth. So the entire output is a truly random output. And so with a truly random function, this generator produces truly random output and is therefore a perfectly secure generator. And so you see how the PRF security property lets us argue security. Basically, we argue that when we replace the PRF with a truly random function, the construction is necessarily secure, and that says that the construction with a pseudo-random function is also secure. Okay, and we're going to see a couple more examples like this later on. So now you understand what a block cipher is, and you have intuition for what security properties it's trying to achieve. And in the next segment, we're going to look at constructions for block ciphers.